So how many of you read chapter 9? The cool thing about this chapter is, although it's about managing multi-user databases, the chapter hits on some really important concepts in computer science in general that will come up in other contexts. Next semester, when you take operating systems, you'll talk a lot more about this as well, because oftentimes operating systems have to solve these same problems of how do we run more than one program at once without making terrible things happen. All right, still doing the right thing. But we're going to look at that general idea in the context of database in this chapter. At least that's the interesting, important part of the chapter to me. So this chapter is about trying to do a lot of stuff at the same time, but making sure you do it correctly. What problems can occur when you're doing things concurrently, and how do you solve those problems? Additionally, we'll look at some details about security. It's pretty important in any context, definitely in databases. And we'll see how transactions are designed and implemented to solve some of the problems related to concurrency and multi-user databases. So you remember this categorization of different kinds of SQL? And in this chapter, we're going to at least begin to look at and slightly consider these two, the data control and the transaction control. So transaction control is the way we define these logical units of work when we have to do kind of a set of SQL commands together as one logical unit of work. Transactions let us encapsulate that. And data control, although we're not going to go into the syntax here, is really the SQL syntax that says this is I can give rights, I can revoke rights or permissions from users. So people may be able to query or update or insert or delete into different tables or views. And we can define all those permissions using a branch of SQL called this data control language. Transaction control is about defining logical units of work, and data control is about defining permissions. The first big principle that I want to throw out at you is atomicity. Atomicity is about doing actions that are completed in an all or nothing kind of sense. Atomicity, or being atomic, an atomic operation is one that either fully happens or doesn't happen at all. We don't halfway do it. Make sense? And we're going to go into some examples of how this may be a problem. So we're going to imagine that when a customer places an order, we have to make 3 changes in our database. We've got to add the order data to the customer table. We have to increase the commissions, the total sales number for the salesperson in the salesperson table. And we have to add an order to the order number, the order table. You see how those are the 3 operations that happen when somebody buys something, that we're going to update all of those records in those 3 tables. What if we do the first 2, but the 3rd operation, the inserting a new order, fails? Because the table's full, the disk is full, there's some weird thing that happens. Step 3 fails because of insufficient space. You see the problem? We've stored part of the actions for the customer where the database shows that somebody bought something, a customer bought something, we're paying our salesman commission, but the customer never gets anything. This is not a good way to run business. This reveals the need for an atomic operation. We either want to do all 3 of those things or none of those things. If we do 0 of them, at least it'll be consistent, and we can try to maybe re-enter them again. We don't want to do 1 or 2 of them. Does that make sense? We have to protect. Make sure we only do all or none. So what we're going to see in this chapter is the idea of transactions as a way of encapsulating a unit of work. So now we have defined there in the middle this transaction, which does all 3 things, all 3 steps, all together. And it's either going to commit the transaction if there aren't any errors, or it will roll back the transaction and undo any number of the 3 that it did. So this is a transaction, and it allows us to implement atomic operations. The next layer that we want to put in here is the idea of concurrency. Concurrent transactions refer to two or more transactions that appear to the user to be being processed simultaneously. So it's as if we're doing two things at the same time. Now, we might actually be doing two things at the same time if we had like a multi-core processor, or it may just be that because of multitasking by the operating system or by the database system, that the transactions are just interleaved in a way that makes them look like they're running at the same time, but really the processor is only doing one thing at a time. So concurrent transactions, concurrency, is the idea of running simultaneous processes. And let me give you an example of that. Imagine that we have user A and B who have both submitted a transaction to be processed by the database. User A reads item 100, changes it, and writes it to the database. It updates item 100. User B does the same process on item 200, reads it, changes it, writes it. So both of those may be like pseudo-simultaneously submitted to the database and processed by the database. But what really happens in the database is this set of 6 steps where you see, interleave the individual steps. Why is this a problem? Well, let's look at this issue called the lost update problem. So this is the same setup, only you see the one difference in user B? It's green, yes. You see the other difference in user B than from the previous example? If they're both trying to read and edit item 100, and we interleave them like so, then what may happen? So we're going to do the read for A. Let's just pretend that the value for A is 7. Sorry, the value for item 100 is 7. That's what's in the table. We then read the item for 100 for B, also 7 is the value. We then decrement the item for A, making it 6, and we write 6 to the database, back to the table. You with me? For A, because we're doing this step 3 for A. Then we decrement item 100 for B, taking the 7 that we had in step 2. The 7 turns into a 6, and then we write it to the database. Do you see what happened? It's like user A's transaction was ignored. Right? We should have decremented it twice because we had 2 transactions that decremented it, but instead we basically lost this update altogether and this decrement because of the way the transactions were processed concurrently in an unsafe way. So this is called the lost update for good reason. So we do not want this to happen. Right? Can you imagine if this were a bank account and instead of decrementing it, we're incrementing, and you had 2 people deposit into your account at the same time, $1,000 each, but your bank account only went up $1,000, not $2,000. You'd be angry, right? You would want that other $1,000. So we don't want this to happen. How do we fix this lost update? What's the solution? Well, one solution that the book discusses is using locks. All right, so what's a lock? The lock, it's a pretty simple idea. It's that we can put a resource lock on some object, whether it may be a table or a row or the whole database, and make sure that nobody else can do any reading or writing. So one type of lock is an implicit lock, and these are locks that are placed by the DBMS, so they're sort of automatic. The other type is explicit, so these are locks that are issued by an application program where the application is in control of when the lock gets placed and when the lock is released. Another term in locks is granularity, and this means how big of an object is locked by the lock, is protected by the lock. So this may be locking a row, so when you have access to this row, nobody else can, or it may be on the size of a table or a view or the whole database. You see the different levels of the lock. The trade-offs there are if you have really large granularity, it makes it easy to avoid conflicts, but is going to really hurt your throughput. Right? If you lock the whole database, then really only one thing at a time can happen, and you would like to be processing as many things at once as possible if you've got a lot of requests coming in. Lastly, the type of lock. This would refer to an exclusive lock, which would prohibit other users from reading the locked resource and writing it. A shared lock, though, would prevent something from being updated, being written to, but still let other people read it. It's generally safer to allow simultaneous shared reads of something, but you don't want two people writing to the same thing. So let me show you an example of explicit locks for concurrent transaction processing. The idea here is we have to issue a lock for the item. In this, you can imagine an item being a row or a table or whatever. That would change depending on the type of lock that it is. So that's sort of a detail that we're glossing over. It kind of seems like it's for a row when we say item 100 though. So this is the same setup as before, but now you have to issue a lock first. So when this is processed at the database server, user A gets the lock on item 100. It's then read. User B tries to lock the item, but it's already locked. So that lock fails, and user B's processing has to wait. If we go back to user A, he can do his thing. That is decrementing the item, taking it to 6, and writing that back to the table. At this point, the lock would be released because user A is done. So now the user B can repeat and try to get the lock for B. This time she'll be able to, and then she can do what she wants to do, which is read it and decrement it and write it back. Another important term that the book introduces is this idea called serializable transactions. So serializable transactions means that there are two transactions that run concurrently, but even though they're running concurrently, they generate the same results as would have occurred if they'd run separately, one first and then the other, or this one first and then this one, running them in serial. Does that make sense? So we usually want to have serializable transactions to make sure that we get the same consistent results regardless of how the transactions may be interleaved and processed by the database server. And one way that this is implemented is through a process called two-phase locking, which is broken out into two phases. In the first phase, the growing phase, locks are obtained, and more locks will be obtained until it has all the locks that it needs. And once the first lock is released, that starts the shrinking phase, and after that point, no other locks can be obtained. So locks are obtained throughout the transaction, but you don't release any of the locks until you either commit the transaction or roll it back. So this is maybe restrictive, but is easier to implement. So this is one way of having kind of this protection when you need to access secure, consistent, safe access to several different resources, is to grow up and then go down. All right, here's the danger in using locks. It's a thing called deadlock, which is also apparently called deadly embrace, which sounds scary. That was in the book. And it means that two transactions are each waiting on a resource that the other transaction holds. So I need something that you have, and you need something that I have, and neither one of us are going to give up what we have. That make sense? So we're kind of caught in this deadly circle that has no end. You kind of understand deadlock in traffic, right? In car traffic, vehicle traffic, where there's just so many people that are blocking each other that nobody can move. The two approaches to deadlock are, number one, preventing deadlock. One way to do this is by requiring users to issue all of their lock requests at one time. Another one is to require programs to lock resources in the same order. And you're going to talk a lot more about this in operating systems. The second way of dealing with deadlock is to let it happen, but detect it and break it. So you have to then, your database has to be looking for situations where deadlock has occurred, where there are these conflicting locks that have been granted, and we have to essentially then abort one of the transactions to free up the locks and get them back so that the other transaction can in fact finish. Let me show you an example of deadlock. Same setup here. Notice it's a pretty simple setup. We're just going to lock an item and read it, and then lock another item and read it. User A does item 100 and then 200. User B does 200 and then 100. So what happens is A gets the lock for 100, B may get the lock for 200. A reads 100. B reads 200. B tries to lock 100, but it can't because that's still locked by A. A tries to lock 200, but it's still locked by B. So neither one of them can finish their set of instructions, their set of 4 instructions, which is the transaction, because they're both depending on the other guy to release a lock that the other one's never going to release because they're waiting on the other guy. So this is bad. And this may not happen all the time, but if there's a possibility of this happening, and then that means there's a possibility of the system getting in a state where jobs can never finish. That's not good, right? We don't want to be in a place where we have these terrible scenarios, even if they're unlikely. So deadlock's a really big deal, and in operating systems and in database systems, we have to go through some procedures, some strategies, some algorithms to try to keep this from happening because it's so deadly, right? It's not really deadly, but it's bad. The authors then present 2 approaches to solving the deadlock problem: optimistic and pessimistic. These are 2 kinds of locking that would assume different things about the potential conflict. In optimistic locking, we assume that no transaction conflict will occur. Basically, we're hoping for the best. And what this means is the database will process a transaction, check whether a conflict occurred, and if it didn't, then the transaction's done. And if something bad did happen, then the transaction is repeated until there's no conflict. The other side is pessimistic, where in pessimistic, you issue the locks before the transaction is processed. So you try to get all your locks first really early on to make sure that nothing bad can happen. When you do this, you get all the locks, you process the transaction and then release them. You're having to hold the locks longer, which is going to slow down the throughput of the system, how much work it can do. So for that reason, the authors say that optimistic locking is preferred for the internet. So as we continue to think about locking, I did want to show you sort of an example. This is an example of a transaction. Essentially, this isn't completely coded out, but in this optimistic approach, notice that we do the select and we do the set quantity equals new quantity minus 5 before we obtain the lock. So we're hoping that that works. That's consistent. There's no conflict in doing that. We're not fighting with some other process, some other transaction when we do this set. In a pessimistic approach, we would get the lock first before we do anything because we're assuming that something bad's going to happen and we're going to keep it from happening. The second difference in this is at the bottom of this optimistic approach, we have to make sure that the update succeeded. If it didn't succeed for some reason, if we had strange values, unexpected from what we did, then we would have to repeat the whole process again. Whereas with pessimistic, you don't have to check and repeat because you know that it worked because you locked first. So how do we declare these transactions? How do we mark boundaries between these logical units of work? This is the basic structure. There's a begin transaction, and then you'd list a set of SQL statements that you want to execute together in an atomic way. At the end, you'd have an if, and then some condition to check if the transaction completed normally. And then you would have these keywords, commit transaction or rollback transaction. All of the major databases have a language like this, although they all have their own kind of different flavor for defining a transaction, for committing it or rolling it back. And what this allows the database to do is it can implicitly set locks based on what tables you use in your transaction. Let's talk a little bit about ACID. ACID is this really important acronym in database, and maybe you've come across it already. I think perhaps it was in that video. ACID stands for atomic, consistent, isolated, and durable. And those are 4 keywords that describe the properties of transactions that we typically want from our database system. Let me show you a little bit about each one. First, we want our transactions to be atomic. We've already said this means we get an all or nothing kind of behavior from the transaction. We do it all or we do nothing. Secondly, consistent. Consistent can be interpreted in a couple different ways, either at the statement level or the transaction level. Statement level consistency means that each statement independently processes rows consistently. So that I summed it up by saying basically we're going to get predictable results. the thing that we expect to happen is going to happen, even if there's some weird changes behind the scenes, sort of related to the interference from other processes. In a transaction level consistency, all the rows impacted by either the SQL statements, by any of the SQL statements, are protected from changes during the entire transaction. So we're protecting it, we're making sure that the transaction has consistent, predictable results, even if there's other potentially interfering things happening at the same time at the database server. Isolated is perhaps the most complicated. It also has to do with this idea of no interference. Every transaction is isolated from the other things that are going on, even though those other things may be manipulating data that's shared between them. The way this has been defined, there are three kinds of errors that can occur, and depending on if those errors are allowed to occur is the way the different isolation levels are defined. So we're going to look at three errors and then show different strictnesses for allowing those errors, and those are going to be the four isolation levels defined by SQL. The first one's called a dirty read, and this means that a transaction reads data that is later rolled back by another transaction. So it reads data from a table that has been changed, but that change hasn't yet been committed. It's later committed and undone, but you've got dirty data. So this is one potential problem. The second one is this non-repeatable read. The non-repeatable read means that the transaction rereads data that has been changed and finds changes due to other committed transactions. So we read at one point during the transaction and got one value, and we read at a different point in the transaction and got a different value. So there's no way we could repeat that first read because it was at a value that was changed in the meantime by some other transaction. The last one is called a phantom read. This means that the transaction rereads data and it finds new rows that were committed by another transaction. So there's just these new rows that appear seemingly out of nowhere. So for those three problems that are possible to exist, the SQL 92 standard defines these four isolation levels. So depending on how much isolation you need, you can choose, depending on your database, one of these isolation levels. And you know that there's trade-offs here, right? That if you're going to require the highest level of isolation, this serializable, then you're going to have to pay a performance price for the database to make sure that that doesn't happen, that there are no phantom reads. You see how this is just incrementally getting bigger. The last piece of asset is durable, and that basically means all the changes that are committed to the database are permanent. They stick, right? They endure. They can't be lost. The last sort of random topic, second to last random topic in this chapter is cursors, where a cursor is a pointer into a set of records. So sometimes it's beneficial for performance reasons to, instead of returning a whole data set to an application, you kind of just return a pointer to a place in the data set and let the user control the movement through that data set. Cursors then, therefore, basically to improve performance. There are four different kinds of cursors that this book discusses. The first one is called forward only, where a forward cursor allows the application to only move forward through the record set. These are going to increase in complexity and cost in terms of performance. The second type of cursor is static. A static cursor processes a snapshot of the relation that was taken when the cursor was opened. And I believe with static, you can go forward or backwards, but you're processing a static snapshot of things. So if the database changes between the time you get the cursor and you read it, then you're not going to get those changes. The third one is called key set. With key set, when you open the cursor, a primary key value is saved for each row in the record set. So you have the primary keys, and whenever you get a row based on that primary key, you actually fetch the latest copy from the database. Whereas with static, you kind of had a whole snapshot of the whole thing. In this one, you get it when you request that row using the cursor. The last one is called dynamic, and this is a fully featured cursor where you can move in any direction. Changes of any type and from any source are visible in the cursor. So if somebody's updating, deleting, inserting into the table, your cursor is going to be able to see those updates, even if you got the cursor long before any of those changes happened. You see, this is the most featured, so it's going to be the most expensive. It's going to be the slowest. I think the general rule is you want to choose a cursor that's at the lowest level possible for your application, because then you'll get the best performance. All right, last topic in this chapter is security. You know this is a big deal. Like Mr. Sokolowski said last time, people are getting hacked all the time, even big name people that have a lot of data. Dig in more depth in any of these, especially if you want to be a security guy or girl. Number one, you certainly want to determine the rights, that is, who has what rights and responsibilities in the database, who can perform authorized activities. Secondly, you should enforce the security requirements using the security features of the database and the application program, so make sure everybody's following the requirements that have been set up. Generally, the security policies are going to limit actions on certain objects to certain users or roles or groups of users. So most of the permissions in the database are going to be set up as this set of users is allowed to have query access on this table. This set of users is allowed to have write access on this table. This set of users can revoke and grant permissions on this table. This is an example for a database they had in the chapter. The role is here, and the tables are up here. So the salesmen have insert, change, and query capabilities, permissions on customer, insert and query on transaction, but only query on work and artist. Whereas the managers have insert, change, and query access on all of the tables. The system admins have grant rights, so they can add other people as they can change the permissions of other users, and they can modify the structure of the table. So you'd have to define what the policies are, and then you would implement them using that branch of SQL, the data control language, DCL. That's how you could set up this structure. So just a quick shotgun approach to security. What I meant was I'm going to just spread a bunch of good tidbits at you all at once. Use a firewall. Run your database behind a firewall to limit exposure, but plan as though the firewall had been breached. Always use the latest security software patches on your operating system and your database and other software that's running. Use the least functionality possible. So you want to make your target as small as possible. That means don't run unnecessary protocols, close ports that aren't being used by those protocols, delete unnecessary system procedures or stored procedures, disable default logins, guest logins. So you really do want to try to make your attack surface as small as possible. So if you're not using something, don't enable it so that people can't hack you through the vulnerabilities of that. Next, physical security, right? You need to protect the actual physical computer that the thing's on if the database matters. Make sure that the database is physically secured behind locked doors. Perhaps that's the easiest way to hack you, right? Someone just comes in claiming to be the janitor, walks in, unplugs your database server and takes it out and has millions of credit cards. Accounts and passwords. This is such a simple thing, but it's sort of like if this is the weakest point in the system, then it's going to get hacked. You want to make sure that users have strong passwords. You want to make sure that users are in the right groups. You don't want people being in groups that they really ought not be in because they have escalated permissions. You want to monitor failed login attempts. You should assign accounts at the lowest privileges possible to make sure people aren't getting too much access to data that they don't really need. And there's 5 tidbits on database security. One specific attack that's really famous that has largely lessened, but it's still something you should know about. It's called a SQL injection attack. Imagine that you're running a web service, a website that's trying to find the employee name based on what you've entered. And then it displays the results of this query on the page. So you're expecting to get a string from the website that's someone's name, like so. And therefore, right, how many rows from the database are you expecting to find? 1. Well, what if someone was a little bit skilled at SQL and instead of typing in Joe Wiley into the input box on the website, instead typed this, closing, sorry, I've got 2 close quotes, or true, semicolon, dash, dash. This is the comment operator. Imagine there's just 1 closing quote here. And how many rows would this return? All of them. And that could be some valuable information to see what all of the employee names are. Imagine it was, imagine we had in this employee table the, the passwords, or we had the salaries. Or imagine it wasn't the employee table, it was a more interesting table. Because we are now able to get everything back, that would give an attacker a lot more information than they ought to have. So this is called SQL injection. So you need to always make sure that when you accept input from a user and use that input in a SQL query, so this is really in the context of the web, you've got to sanitize the input and make sure it doesn't have SQL commands in it. This is the best comic on this. I don't know if you've seen this, Little Bobby Tables. You can read this if you haven't read it before. Because this is such an old attack, most frameworks like ASP.NET or PHP, they have automated ways of checking to make sure that it's valid input. But you need to make sure that you're doing it. In this chapter, we've seen that there are some problems when we have multi-user databases, and we've tried to solve some of those problems. So we understand now a little bit of how the database handles concurrent transaction processing and the basics of security in databases. Overall, what I want you to remember from this lecture is that databases have to allow a lot of people to use the database, but keep bad things from happening, which they could if we're not careful in the way that we design and implement the database. A lot of this stuff is already implemented behind the scenes in the database to make sure that things that run concurrently don't mess everything up. But as computer scientists, you need to know that these problems are out there and that when you're working in a concurrent world, which you often will be, bad things can happen and you need to be anticipating the complexities of concurrency and be familiar with some of the solutions to solve them, like locks. And you'll talk about this and other solutions in operating systems where it's a really old, well-studied problem. So we've seen concurrency and security, 2 really important features in a database.